All right, so we have a function to look at here, a linear function, and we want to set up a middle Riemann sum or a Riemann sum on the midpoints of all these intervals. So let's start setting this up. So let's just kind of handle this in order here. We want to clearly identify delta x. So how do we find delta x? Actually, before we start doing this stuff, let's set up a graph here. May not be terribly accurate like usual, but it's helpful to organize. So x-axis 1, 2, 3, 4, 5. We're gonna go high as 20, 4 is 19, I think. Yeah, 3 times 5 plus 4 is 19. Okay, so at x equals 2, I think y is equal to 10. At x equals 5, y is equal to 19. We know this is a straight line that joins these 2 points. All right, so this is the area we're going to be dealing with. All right, so let's find the value of delta x. So basically for a midpoint Riemann sum, we want all of the subintervals of 2, 5 to be the same width. So let's just take this interval and divide it appropriately. So the width of the full interval will be 5 minus 2, which will be 3. And I want to divide that by 4. So that'll give me a delta x of 3/4 or 0.75. Okay, so now that we have those, add this to our graph. Based on each one of these intervals is going to be 3/4 of a unit long. So while we're at it, let's go ahead and identify what our values are. X0, x1, x2, x3, x4. X0 and x4 are going to be the ends of the interval, so 2 and 5. And the way I'm going to get the intermediate values here are, what's 2 plus a single delta x? That'll be 2.75. And then the next one, what's 2 plus 2 delta x's? That'll be 3.5. So 3.5. And then 2 plus 3 delta x's will be 4.25. Okay, so I think I've divided this up appropriately, but I'm doing a midpoint sum, so I don't really need to know. I mean, I need to know, but I'm not going to make my calculations for this Riemann sum on these values x0 through x4. So what I'm actually going to need are these values: x1 bar, x2 bar, x3 bar, and x4 bar. And maybe I should sort of partition these things off. So where is x1 bar? X1 is going to be the midpoint of x0 and x1. So 2 plus 2.75 over 2. So that's 4.75 over 2, or 2.375. So halfway across that interval is where I'm going to sample. So call that, oh, let's not do that. So basically, I want to think of this first interval. I'm going to treat it like a rectangle and find that area. All right. So now let's find the next value. So what's the midpoint of x1 and x2? That will be 2.75 plus 3.5. Yeah, 3.5 over 2. So that's 6.25 over 2, which will be 6.25 over 2. 3.125. So something else I want to point out here is that if you take x1 bar and add a delta x to it, let's do it right, make sure to give myself a little bit of a check. 2.375 plus 0.75, I get 3.125. So your delta x's should separate your boundaries. They should also separate the midpoints from each other. Now, I'm actually going to use that information to find these next two values. 3.175 plus delta x equals 3.875. And then 3.875 plus delta x is equal to, having trouble with this, 3.875 plus 0.75, 4.625. So these are my sample values. So now that I have those sample values, let's go ahead and keep sketching out the rectangles here. So I'm not going to find the area of these like different trapezoids. I'm going to find the area of these rectangles. So how do I do that? M4 is going to be equal to the sum of 4 different areas. So how do you find the area of a rectangle? Well, it's the width, which in this case is, or in any case, is delta x times the different heights. So times f of x1 bar plus f of x2 bar plus f of x3 bar plus f of x4 bar. So what is delta x? That is 0.75. What is f of x1 bar? So x1 bar is 2.375. So I want to multiply that by 3 and add 4 to it because that is what our function is, 2.2375. So 2.375 times 3 plus 4 is 11.125. And then f of x2, so 3.125 times 3 plus 4, that's 13.375. And then f of x3, 3.875 times 3 plus 4, that is 15.625 plus f of x4, so 4.625 times 3 plus 4, 17.875. All right, so now I want to add all those together. So 11.125 plus 13.375 plus 15.625 plus 17.875. And I get a grand total of 58. But then I don't want to just add all those heights together. I want to now multiply that by 0.75, which is the value for delta x. And now I get a value of 43.5. So again, let me shade in the area I found here for just one of these rectangles. I found the area of this rectangle, not the trapezoid that actually exists for this function, but that rectangle I made to approximate it. So have I done everything that this question has asked me to do? So I found delta x, I found the location of all my sample x values. Okay. All right, that looks good. Moving on. Use a familiar geometric formula to determine the exact value of the area. So let's kind of recreate at least the geometric figure here. So this is the area I actually wanted to find. Now I'm going to use geometry on it. So what is this? This is a trapezoid. So how do I find the area of a trapezoid? The area is equal to 1/2 times the base times height 1 plus height 2. And I think this might be a little different than what I showed you in a previous question where I found the area of a trapezoid. I think I might have averaged the bases, so I did base 1 plus base 2. It doesn't really matter, but in a trapezoid, you're going to have to average two different values, either for the base or the height. The way I've drawn this trapezoid, that's going to be for the height. So let's go ahead and find these values here. What is the base length of this trapezoid? Well, if you go to our graph, this is 3 units long. Because the interval we're actually integrating over, or doing a Riemann sum over, is 3. So our base units, our base length is 3. What is this first height? I believe we said that was 10 because f of 2 was equal to 3 times 2 plus 4. So this is 10. And I think the other one we said was 19. If you plug in 5 for x, you get 19. So 1/2 times 3 times the quantity 10 plus 19. So I get 1/2 times 3 times 29. What does that come out to be? Comes out to be 43.5. How does that compare with what we got? So our approximate sum is exactly equal to, the exact area in this curve. So why did that happen? So part C, explain why the values compared to A and B turn out to be the same. So let's look at the graph we drew. So if we look at any one of these rectangles, we can see that we have two different areas where we have error, right? I'm finding the area of this little triangle in here, even though that little area does not belong to, basically it's not under the curve we're trying to approximate the area underneath. But if you look to the right of the midpoint, we have another little triangle here whose area is under our curve, but we didn't find that area. And because we have a straight line here, those areas are going to be identical. So basically I have an over in every single part of in every single subinterval, I have an overestimate and an underestimate that are exactly the same size. They're going to cancel each other out. So because of that, that's why those areas turn out to be the same. Will this be true if we use a different number other than n equals 4 and compute the midpoint? Well, let's think about it. If we go back to our original graph here, what if instead of drawing 4 rectangles like this, I drew 8? Let's take the last rectangle here, and I'm just gonna do 1. Otherwise, it's gonna get very cluttered. But let's split this one in half. If we do that, what do our two midpoint rectangles look like here? So pretend I was able to do this as accurately as I wanted. Now that's better. But even though I've made them smaller now, I'm still going to have the same overestimate and underestimate. They're going to be the same size as each other. They're going to cancel each other out. So I think because of that phenomenon, it doesn't matter how many intervals I split this into. I'm not going to be able to escape the fact that I'm going to have those overestimates and underestimates that cancel each other out. So I don't think it matters that I'm using 4 rectangles as opposed to anything else. Really, I could just be 1. And in fact, to illustrate the fact that it could be 1, let's go look at my trapezoid here. Let's do an M1. If I was going to do a midpoint approximation on this trapezoid, at one place. So there's my midpoint. So I'm gonna make a rectangle like this. What's the area of this rectangle I just made? Well, the area is going to be still a base length of 3. What is the height now going to be? Well, this is a linear function, so the height is going to be the midpoint of 10 and 19. So 10 plus 19 over 2. And hopefully you're seeing some parallels between the way these two things look. This is still going to come out to be 43 and a half. What else are we asked about part C? Will L4 or R4 have the same value as the exact area? So let's draw the trapezoid again. So instead of now, I still want to split it up into 4 subintervals, but now I want to take left rectangles, which means my rectangles are going to look like this. So now if I take the area of those rectangles, how do the area of those rectangles, how is that going to be related to the area of the trapezoid? So now you can see I'm going to get all these little triangles on top here that I'm not finding these areas. And unlike with the midpoint sums, there's not some other area I'm finding that's outside of this, that's outside of this area that's going to cancel out. So because of that, L4 is going to have errors built into it, and they're going to be overestimated. I'm not going to draw this for you, but if you need to convince yourself, I would encourage you to draw the right end rectangles to see that those are all going to be overestimates. You're going to end up finding the areas of these little small triangular regions that don't live under the curve. So to answer your final question in part C, L4 and R4 will not have the same value. And finally, D, describe the collection of functions G for which it will always be the case that n, so the midpoint Riemann sum, regardless of the value n, gives the exact net signed area. So here's something we can say. I think no matter what kind of linear function I have, that midpoint Riemann sum is going to basically be acting on trapezoid. You're going to get the exact value of your area. But can we open it up? Can we be more inclusive in that? Does the function have to be linear for this to work? So let's look at this thing again here. So I'm going to get rid of all my scribbles. So this trapezoid here, what was the bottom line here? Let's just do this in 2 intervals because I think this will illustrate what I want. So if I draw a midpoint rectangle here and a midpoint rectangle here to set up a Riemann sum. So hopefully I've convinced you by now that a linear function, a midpoint Riemann sum will give the exact same area as what's actually there. But what if this function is not actually linear? Remember, what did we say like the secret ingredient was really? Is that you had some area that was being overestimated on part of the function and underestimated on the other. I think if I joined these 2 points with any function that looked like that, this might be harder to do than no, that's not even the midpoint. So let's mark the midpoint. Still not very good, is it? So what I'm trying to do is this. I'm trying to make this area and this area equal. And I think that's probably about as inclusive as we can be, is that if you have a function so where you have these overestimates and underestimates on area are the same, then you're also going to get the same, basically your midpoint Riemann sum is going to give you the same answer as whatever the exact answer is. So I will say without a doubt that any linear function you'll get this result on. But I think we could open a little more. I think it's just a little harder to describe, what the condition is.